Hello and welcome back to Sleepy Darwin. Whether you're here to quiet your mind, to ponder life's biggest mysteries, or simply to drift off while contemplating the infinite, you've found exactly the right place. Tonight, we're exploring a question that sounds like science fiction but is unfolding in laboratories around the world right now. What if death, at least for our cells, was actually optional? We'll meet jellyfish that turn back time, cells that forgot how to die, and scientists working late into the night, searching for secrets that nature has hidden in the smallest corners of life. From the warm waters where immortal creatures drift, to the test tubes where human cells divide endlessly, this is a story about the choice between forever and today. Now, before we begin this cellular journey, I have a small favor to ask. If these gentle explorations help you find peace at the day's end, a like and a subscribe would mean the world to this voice in the darkness. And please, share in the comments where you're tuning in from and what time it is in your corner of the world. Are you listening from a bustling city where cells never sleep, or perhaps a quiet room where everything slows down? As always, I hope this video isn't too fascinating to let you sleep. But if you do find yourself wide awake, at least you'll be pondering one of life's most profound questions. Why do cells choose to die when they might not have to? So settle in, take a deep breath, and let's explore the microscopic universe within you. What does it mean to die? It's a question that might seem heavy for a bedtime story, but I promise you we're going to explore it gently, like examining sea glass on a moonlit beach. Because death, especially at the cellular level, isn't the ending we might imagine. It's something far more nuanced, far more beautiful, and dare I say, far more alive than we've been led to believe. Let's start by zooming in. Way in, past what your eyes can see, past what even a regular microscope can reveal. We're going to the cellular level, where the rules of life and death play out quite differently than they do for you and me, lying here under our blankets, breathing slowly, existing as whole beings. You see, while you, the complete, wonderful you, will someday cease to be, parts of you are dying right now, right this very second, as you listen to my voice. And that's not scary. It's actually miraculous. Because you're also being reborn, cell by cell, moment by moment. You're less like a statue, fixed and unchanging, and more like a river, constantly flowing, constantly renewing, the same and yet never the same. At the organismal level, that's the whole you. Death seems pretty final. One day, hopefully far in the future, your heart will beat its last beat, your lungs will exhale their final breath, and the extraordinary pattern that is, you will dissolve back into the universe from which it came. But at the cellular level, oh, that's where things get interesting. Some of your cells live for mere days. The cells lining your gut, for instance, they're like mayflies of your internal world, living fast and dying young, replaced every 3 to 5 days. It's exhausting work, being a gut cell, constantly exposed to everything you eat and drink, defending you from invaders, helping you absorb nutrients. They burn bright and brief, these cellular heroes. Then there are your red blood cells, carrying oxygen on a 120-day journey through the highways and byways of your circulatory system. Imagine them as tiny ships, sailing through your bloodstream for 4 months, before finally docking at their final port in your spleen or liver, where they're gently dismantled and recycled. Your skin cells? They live about 2 to 3 weeks, constantly pushing upward from the depths of your epidermis, like slow-motion fireworks, until they reach the surface and flake away. Every time you run your hand across your face, you're touching cells that are preparing for their final bow. And then there are the neurons in your brain. Many of them are as old as you are. They've been with you since before you were born, witnessing every moment, storing every memory, sparking every thought. They're the keepers of your story, the ancient librarians of your personal history. But here's where our story takes a profound turn. This cellular death I'm describing, it's not random. It's not chaotic. It's choreographed with the precision of a ballet, the timing of a symphony. Scientists call it apoptosis, a word that comes from ancient Greek, meaning falling off, like leaves from a tree in autumn. And just like those falling leaves make room for new growth, cellular death makes room for cellular life. And here's the truly mind-bending part. Theoretically, Turritopsis dornii can do this forever. It can cycle from polyp to medusa, around and around, like a cosmic carousel that never stops spinning. In laboratory conditions, researchers have observed individual jellyfish performing this miracle of rejuvenation dozens of times. In the wild ocean, who knows? There could be jellyfish out there that have been cycling through life stages since before humans invented writing. Of course, I should whisper a small truth here. Immortal doesn't mean invincible. These jellyfish can still be eaten by predators, succumb to disease, or face environmental catastrophes. They're not immune to the dangers of ocean life. But left to their own devices, with enough food and the right conditions, they simply don't age to death. They refuse the cellular surrender we talked about in the last chapter. They've found a loophole in the contract of mortality. But our immortal jellyfish isn't alone in defying death's expectations. Let me introduce you to another character in our story of cellular rebellion, Hydra vulgaris. Don't let the name fool you. This isn't the mythological monster with multiple heads that grow back when cut off, although, actually, that's not too far from the truth. Hydra is a tiny freshwater animal, a polyp no bigger than a rice grain, that lives in ponds and slow-moving streams. It looks like a miniature sea anemone, a slender tube with tentacles on top, waving gently in the current. And like its mythological namesake, Hydra seems to have conquered death through the power of regeneration. But Hydra's immortality works differently than our jellyfish friend. Hydra doesn't cycle through life stages. Instead, it simply doesn't age. At all. Scientists have kept Hydra in laboratories for years, watching, waiting for signs of senescence, the cellular aging we expect in all living things. But Hydra just keeps on keeping on, budding off identical copies of itself, maintaining its cells in perpetual youth. The secret? Hydra is made almost entirely of stem cells. Now, stem cells are like the cellular equivalent of unmolded clay. They can become any type of cell the body needs. Most animals, including us humans, have stem cells when we're developing, but they become scarce as we age. It's like we use up our clay making the sculpture of ourselves, and once it's fired in the kiln of development, that's it. We're stuck with the shape we've got. But Hydra never runs out of clay. Its body is constantly replacing itself with fresh stem cells. Every cell can divide indefinitely. Every part can regenerate. Cut a Hydra in half, and you don't get a dead Hydra. You get two Hydras. It's less like an animal and more like a living, self-maintaining system of cellular potential. And then there are the planarian flatworms, perhaps the most remarkable regenerators of all. These little flatworms, some no bigger than a comma on this page you're not reading because your eyes are closed, possess regenerative abilities that seem to mock our understanding of biology. Cut a planarian in half, and both halves will regenerate into complete worms. Cut it into 3 pieces, 4 pieces, even dozens of pieces. As long as each piece is large enough, about 1/2 79th of the original worm, scientists have calculated with amusing precision, each will grow into a full flatworm. It's like each fragment contains a blueprint of the whole, a cellular memory of what it means to be a complete planarian. But here's where it gets even stranger. Planarians can regenerate their brains, their entire brains. Think about that for a moment. If you cut off a planarian's head, the tail will grow a new head, complete with a functioning brain. But what's in that brain? Does it remember being part of the original worm? Does it have the same personality, if flatworms can be said to have personalities? Scientists have actually tested this. They've trained planarians to navigate mazes or respond to light, then cut off their heads. When the new heads grow back, the worms still remember their training. Somehow, the memory persists, even without the original brain. It's as if memory in these creatures isn't stored in one place, but distributed throughout their entire being. Now, I know what you're thinking, lying there in the dark. You're thinking, these are all very simple creatures. What about something more complex? What about something that faces the kind of challenges that would make immortality actually impressive? Well, let me tell you about the tardigrade. And perhaps that's the most comforting thought of all, that death, at least at this scale, isn't an ending but a transformation. Those gut cells that die after a few days, their components are recycled, becoming part of new cells. The iron from your old red blood cells becomes part of new ones. Even in death, your cells contribute to your life. We are, each of us, a paradox wrapped in skin and wonder. We are dying so that we might live. We are changing so that we might remain ourselves. We are finite beings made of finite parts. Yet somehow, through the magic of organized cellular death and birth, we persist. As you drift closer to sleep, carried on these thoughts like a leaf on a gentle stream, remember this: you are not just alive. You are a liveness itself, a process, a pattern, a persistence. You are trillions of tiny lives, coordinating their individual stories to tell the larger story of you. And in that story, death isn't the villain. It's just another character, playing its necessary role, keeping the narrative moving, making space for new chapters to be written in the book of you. Tomorrow, when you wake, about 50 billion of your cells will have died while you slept, and roughly the same number will have been born. You'll stretch and yawn, and be remarkably, miraculously, still you, the same river, made of entirely different water, flowing on toward another day. Now, let me tell you a story. A true story, though it sounds like something from a fairy tale. In the warm waters of the Mediterranean Sea, and now in oceans all around the world, there drifts a creature no bigger than your pinky nail. It's transparent, delicate, with a red stomach that looks like a tiny ruby suspended in crystal. Its name is Turritopsis dornii, but you might know it by another name, the immortal jellyfish. And when I say immortal, I don't mean it lives for a very long time. I mean it can literally reverse its aging process and start over. Imagine if you, lying there in your bed, could decide, you know what, I think I'd like to be a baby again. And then, you actually did it. Every cell in your body reversing course, unwinding the clock, returning to the beginning. That's what this little jellyfish can do. The story of how we discovered this remarkable ability reads like a detective novel. In the 1982nd, a German marine biology student named Christian Sommer was studying hydrozoans, tiny marine creatures, in the Italian Riviera. He collected some Turritopsis specimens, bringing them back to his lab to observe their life cycle. Like all jellyfish, they were supposed to spawn, release their genetic material into the water, and then die. It's the way of things, the ancient contract between jellyfish and the sea. But these jellyfish, they didn't read the contract. Instead of dying after reproduction, something extraordinary happened. They began to change, not growing older, but growing younger. The adult medusa, that's the bell-shaped form we think of as a jellyfish, started to contract. Its tentacles retracted, its bell inverted. And slowly, miraculously, it transformed back into a polyp, the juvenile stage of its life cycle, like a butterfly deciding to become a caterpillar again. Let me paint you a clearer picture of this magic, because it truly is magical, even though it's completely scientific. When a Turritopsis jellyfish faces stress, maybe the water's too warm, maybe it's injured, maybe it's simply getting old, it can initiate a process called transdifferentiation. Now, that's a word that might make your sleepy brain stumble. So let me break it down into a bedtime story. Imagine each cell in your body is a actor who's been playing the same role for years. Your skin cells have been playing skin cell since they were born. Your muscle cells have been playing muscle cell. They know their lines, they know their marks, they're comfortable in their roles. But what if, and here's where it gets wild, what if those actors could suddenly decide to audition for completely different parts? What if your skin cell could say, you know what, I think I'd like to try being a nerve cell today. That's transdifferentiation. The cells of the immortal jellyfish can change their fundamental identity. A muscle cell can become a nerve cell. A nerve cell can become a reproductive cell. It's like every cell contains the entire script of the jellyfish's life, and they can flip to any page, play any part. When the jellyfish transforms from medusa back to polyp, every specialized cell in its body can de-differentiate, forget its specialty, and then redifferentiate into whatever type of cell the polyp needs. It's not just healing. It's not just regeneration. It's a complete cellular career change, a biological reboot. Tardigrades, also called water bears or moss piglets. Isn't that delightful? Aren't technically immortal, but they've achieved something perhaps even more impressive. They're virtually indestructible. These microscopic animals, looking like tiny eight-legged bears in slow motion, have survived conditions that would instantly kill almost any other living thing. Freeze them to near absolute zero, they survive. Heat them to 300 degrees Fahrenheit, they survive. Expose them to radiation levels 1,000 times what would kill a human, they survive. Send them to space, expose them to the vacuum and cosmic radiation, yes, they survive. They've been found in the Himalayas, in deep ocean trenches, in hot springs, in Antarctic ice. How? When conditions become unbearable, tardigrades enter a state called cryptobiosis. They expel almost all the water from their bodies, curl up into a little ball called a ton, and essentially pause. Their metabolism drops to 0.01% of normal. They're not dead, but they're not really alive either. They're in a state between states, waiting for better times. And they can wait. Oh, how they can wait. Tardigrades have been revived after decades in cryptobiosis. Some scientists speculate they could survive centuries, maybe millennia, in this suspended state. They've turned the temporary pause button that some cells have into a full stop and start remote control for their entire being. So what makes these creatures special? What cellular secrets have they unlocked that the rest of us haven't? For our immortal jellyfish, it's the ability to fundamentally change cellular identity, that transdifferentiation we talked about. Most animals develop along a one-way street. Stem cell becomes specialized cell, and that's it. But Turritopsis found a way to make that street two-way. It's like having a time machine, but only for cells. For Hydra, it's about maintaining a fountain of youth in the form of stem cells. While most of us carefully ration our stem cells, using them up as we develop and grow, Hydra keeps the factory running. Every cell division is as perfect as the first. No accumulation of errors, no cellular exhaustion, just endless, perfect renewal. For planarians, it's about distributed intelligence and extreme regenerative capacity. They've spread the instructions for being a worm throughout their entire body. Every piece knows how to rebuild the whole. It's like having backup copies of yourself stored in every cell. And for tardigrades, it's about the ultimate pause button. When life becomes unbearable, they don't die, they wait. They've mastered the art of metabolic patience, of cellular suspended animation. But there's something else these creatures share, something that goes beyond the cellular mechanisms. They all live in relatively simple environments with specific pressures that made these abilities advantageous. The immortal jellyfish lives in the ocean, where being able to revert to a younger stage means surviving lean times or escaping danger by becoming small again. Hydra lives in fresh water, where being able to bud off copies of yourself is a great way to colonize a pond. Planarians live in dark, wet places where being able to regenerate from fragments means surviving predation. And tardigrades live everywhere, so being able to survive everything is their superpower. Evolution doesn't create these abilities for fun. Each represents millions of years of trial and error, of countless generations facing death and occasionally, miraculously finding a way around it. These aren't accidents. They're answers to very specific questions posed by the environment. There's one more secret I should share with you about these biological immortals. It's about telomeres, those protective caps on the ends of chromosomes I mentioned earlier. Think of them like the plastic tips on shoelaces. Every time a normal cell divides, these telomeres get a little shorter. When they get too short, the cell can't divide anymore. It's one of the ways our cells count down to death. But many of these immortal creatures have found ways around the telomere problem. They produce an enzyme called telomerase that rebuilds the telomeres, refreshing the cellular clock. It's like having a shoelace that repairs its own plastic tips. The countdown never reaches zero. In humans, most of our cells stop producing telomerase after we're born. Only a few cell types, like stem cells and, unfortunately, cancer cells, keep making it. But these immortal creatures? They've kept the telomerase factory running. Their cells can divide indefinitely without wearing out their chromosomes. As you lie there, perhaps drifting closer to sleep, consider this. Somewhere in the ocean right now, there's a jellyfish turning back time. Somewhere in a pond, a hydra is budding off a perfect copy of itself, as it has for who knows how many years. Somewhere in a drop of water on moss, a tardigrade is waking up from a decades-long sleep, ready to face whatever the world has become. These creatures have found different answers to the same question. How do we persist? How do we continue? They've each discovered a unique way to thumb their nose at death, to refuse the cellular surrender that seems so inevitable to the rest of us. But here's a thought to carry into your dreams. These creatures paid a price for their immortality. The jellyfish gave up complexity. It's beautiful, but simple. Hydra gave up the ability to be anything more than a tiny polyp. Planarians gave up the security of centralized systems. And tardigrades, for all their invincibility, gave up the ability to do much more than survive. We humans, we chose a different path. We chose complexity over immortality, chose to burn bright rather than burn forever. But by studying these immortal wonders, by understanding their secrets, we might find ways to have both, the complexity of human life, with just a touch of jellyfish time-turning, a dash of hydra regeneration, a sprinkle of tardigrade resilience. But that's a story for another chapter, another night, another dream. Now I want to tell you a different kind of story. Not about jellyfish in distant oceans or tiny creatures in forgotten ponds, but about a woman named Henrietta Lacks. She was born in 1920-inch Roanoke, Virginia, and she loved to dance. She painted her nails red, she cooked for her family, she grew up picking tobacco, and later moved to Baltimore with her husband and 5 children. She was, by all accounts, a woman full of life and laughter. And though Henrietta died in 1951 at the age of just 31, her cells are still alive today. They're alive in laboratories across the world, in space stations orbiting our planet, in research facilities on every continent. Her cells have been alive now for far longer than she ever was. They've touched more lives, traveled more miles, and contributed to more discoveries than any human cells in history. This is the story of HeLa cells, the first human cells to achieve immortality outside the human body. But it's also a story about what we owe each other, about the price of scientific progress, and about what it means to live on in ways we never imagined. Henrietta's story begins, as too many stories do, with pain. In January 1951, she felt a knot in her womb. A knot, she told her cousins, using the kind of simple, honest language that defined her. She was a young mother, with a baby not yet 1 year old, and she knew something wasn't right. The local doctors in her predominantly black neighborhood couldn't help her, so she went to Johns Hopkins Hospital in Baltimore, one of the few hospitals that would treat black patients in that era of segregation. There, Dr. Howard Jones examined her and found what Henrietta had felt, a tumor on her cervix, about the size of a nickel, glistening and purple-red, like nothing he'd seen before. In those days, cervical cancer treatment was crude by today's standards. Radium tubes sewn into fabric pouches and placed inside the body, burning away the cancer, but also damaging healthy tissue. Before beginning this treatment, and without asking Henrietta's permission, because in 1951, doctors rarely asked, a surgeon named Dr. Lawrence Wharton Jr. took 2 small samples of tissue, one from the tumor, one from the healthy cervix nearby. These tissue samples, each no bigger than a sesame seed, were sent down to the hospital's tissue culture lab, run by a researcher named Dr. George Gay, pronounced Guy. Now, Dr. Gay had been trying for decades to grow human cells outside the human body. He dreamed of having human cells that could live in petri dishes, allowing researchers to study diseases and test treatments without experimenting on people. But every sample he'd tried had died within days or weeks. Human cells, it seemed, simply couldn't survive outside their natural home. Dr. Gay's assistant, Mary Kubitschek, handled Henrietta's samples like she'd handled hundreds before. She placed them in test tubes with a nutrient solution, a special recipe doctor. Guy had developed, with chicken plasma and beef embryo extract, the cellular equivalent of comfort food. She labeled them HeLa, the first 2 letters of Henrietta's first and last names. Then she placed them in an incubator and waited for them to die like all the others. But Henrietta's cells didn't die. The next morning, Mary checked the tubes and saw something unprecedented. The cells hadn't just survived, they doubled. Where there had been 1 cell, now there were 2. Where 2, now 4. They were growing with a vigor no human cells had shown before in culture. Dr. Gay could hardly believe it. He watched day after day as the cells continued to multiply. They filled one test tube, then two, then dozens. Within weeks it was clear. These cells were different. These cells were immortal. But while Henrietta's cells thrived in the laboratory, Henrietta herself was dying. The cancer was aggressive, more aggressive than anyone had imagined. The radiation treatments that were supposed to save her life instead seemed to make little difference. The tumor grew and spread with terrifying speed. By August, just 8 months after her diagnosis, tumors had colonized her entire body. Her kidneys failed. She needed blood transfusions. The pain became unbearable. On the 4th of October, 1951, at 12:15 a.m., Henrietta Lacks died. She was buried in an unmarked grave in her family cemetery in Clover, Virginia. Her husband and children mourned. Her cousins grieved. And in laboratories beginning at Johns Hopkins and soon spreading across the world, her cells lived on. What made Henrietta's cells different? Why did they achieve what no other human cells had managed? The ability to live and divide indefinitely outside the body. The answer lies partly in the nature of cancer itself, and partly in the specific, terrible efficiency of Henrietta's particular cancer. You see, normal cells have built-in limits. Remember those telomeres we talked about? The protective caps on chromosomes that shorten with each cell division? Normal cells also have checkpoint systems, like quality control inspectors, that monitor each division. If something goes wrong, if the DNA is damaged or the cell divides too many times, these checkpoints trigger cell death. It's a safety system, preventing damaged cells from taking over. But cancer cells are cellular rebels. They've figured out how to bypass these safety systems. Henrietta's cancer cells had multiple mutations that made them particularly adept at survival. They reactivated telomerase, that enzyme that rebuilds telomeres, allowing them to divide indefinitely without their chromosomes fraying. Like a clock that forgot how to tick forward, they lost track of time. They also ignored the normal signals that tell cells when to stop dividing. Imagine if your cells were like well-behaved students who raise their hands and wait to be called on. Cancer cells are like students who shout out answers, push to the front, take up all the space. They've forgotten the cellular manners that keep our bodies in balance. But HeLa cells went beyond typical cancer cells. They had an unusual number of chromosomes. Instead of the normal 46, they had around 82. This condition, called aneuploidy, would usually be fatal, but somehow Henrietta's cells made it work. They were genetically chaotic but functionally robust, like a jazz improvisation that breaks all the rules but somehow creates beautiful music. They also grew faster than any human cells researchers had seen. While normal cells might divide once every day or two, HeLa cells could divide every 20 to 24 H-hours. In the nutrient-rich environment of the laboratory, free from immune system attacks, they flourished like a garden with no seasons. Eternal spring, eternal growth. And they were hardy. You could freeze them, thaw them, ship them around the world, and they'd bounce back. They could survive conditions that would kill other cells. They were the cellular equivalent of those pioneers who crossed continents and oceans, adapting to whatever new environment they encountered. Dr. Gay quickly realized what he had. These cells could transform medical research. He started sharing them with colleagues, first at Hopkins, then at other institutions. In an era before strict biological material transfer agreements, he gave them away freely. Want to study viruses? Here, try these cells. Working on cancer? Take some HeLa. Developing vaccines? HeLa cells could help. The timing was perfect. This was the early 1952 when Jonas Salk was developing the polio vaccine. Testing the vaccine required huge numbers of cells susceptible to the polio virus. HeLa cells proved perfect for the job. They could be infected with polio, they grew quickly enough to meet demand, and they were standardized. Every lab could use the same cells, ensuring consistent results. A HeLa factory was established at the Tuskegee Institute. Yes, the same Tuskegee where, in a terrible irony, unethical medical experiments were being conducted on black men. But the HeLa production facility was different. It employed black scientists and technicians. producing millions of cells that would help create a vaccine to save countless lives, including many black children who were disproportionately affected by polio. The contributions of HeLa cells to medicine read like a greatest hits album of 20th and 21st century biomedical achievements. They went to space in the 1962nd to study the effects of zero gravity on human cells. They were used to map the human genome. They helped develop drugs for HIV, AIDS, cancer, Parkinson's disease, and influenza. They were instrumental in developing in vitro fertilization techniques. Scientists have used them to study how cells age, how viruses infect us, how radiation affects human tissue. If you've received almost any vaccine in the last 70 years, HeLa cells probably played a role in its development or testing. If you've taken medication for a serious illness, HeLa cells likely helped ensure its safety. They've saved millions of lives, prevented countless cases of disease, and advanced our understanding of human biology in ways that would have seemed like magic to previous generations. By some estimates, scientists have grown 50 million metric tons of HeLa cells. That's more than 400 times Henrietta's body weight, replicated again and again in laboratories around the world. Her cells have been bought and sold, patented and profited from, used in research that has generated billions of dollars. And yet, for decades, Henrietta's family knew nothing about any of this. They didn't know her cells had been taken. They didn't know her cells were still alive. They didn't know her cells had traveled the world, contributed to Nobel Prize-winning research, or helped save lives. They found out in the 1972nd, more than 20 years after Henrietta's death, when researchers contacted them seeking blood samples to better understand HeLa genetics. Imagine that moment. You're Henrietta's daughter, and you get a call from someone saying your mother's cells are still alive. Your mother, who you watched die when you were just a child, whose absence has shaped your entire life. Her cells are not just alive but famous. They're in laboratories everywhere. Scientists know more about your mother's cells than you know about your mother. The family couldn't afford health insurance, couldn't afford the treatments that had been developed using Henrietta's cells. The injustice of it was sharp and clear. Henrietta's cells had generated wealth and medical breakthroughs, but her family struggled to access basic healthcare. This raises profound questions about consent, ownership, and justice. Henrietta never agreed to have her cells taken for research. In 1951, this was standard practice. Doctors took samples without asking, especially from poor patients, especially from black patients. The medical establishment saw it as waste, not, want not. But those samples were pieces of people, carrying their genetic information, their biological essence. Today, we have informed consent procedures. We have institutional review boards. We have ethics committees. But these exist largely because of cases like Henrietta's. Because we learned, sometimes painfully, that medical progress shouldn't come at the cost of human dignity. And yet, the questions remain complex. If Henrietta's cells hadn't been taken, how many people who are alive today wouldn't be? How many discoveries wouldn't have been made? Can we celebrate the good that came from HeLa cells while acknowledging the wrong of how they were obtained? Can both truths exist simultaneously, like cells that are both dying and living? There's another layer to this story, one that brings us back to our central question about cellular immortality. HeLa cells are immortal, yes, but are they still Henrietta's? They've been living in laboratories for more than 70 years. They've mutated, evolved, adapted to their artificial environment. They've been exposed to viruses, chemicals, and conditions Henrietta never encountered. Scientists debate whether HeLa cells should even be classified as human anymore. They're so different from normal human cells that some have proposed calling them a new species. This is the paradox of cellular immortality. The cells live forever, but do they remain themselves? HeLa cells carry Henrietta's genetic material, but they no longer function like the cells in her body. They can't form tissues or organs. They can't create the complex structures that made Henrietta who she was. They just divide and divide and divide, eternal but limited, alive but not living in any way Henrietta would recognize. It's like having a single note from a beautiful song played forever. The note continues, but the melody is lost. The rhythm is gone. The harmony that made it music has disappeared. Is that immortality? Or is it a kind of cellular purgatory? In recent years, there have been efforts to recognize Henrietta's contribution and address some of the injustices. The Johns Hopkins Institute for Clinical and Translational Research is housed in the Henrietta Lacks Memorial Building. The Henrietta Lacks Foundation provides scholarships and healthcare assistance to her descendants. In 2021, the World Health Organization honored Henrietta, with the Director General saying she transformed medical science and acknowledging that her story reflects the injustices of racism and inequality in healthcare. The Lacks family has also gained some say in how Henrietta's genetic information is used. In 2013, when researchers published the HeLa genome without consulting the family, it sparked discussions that led to an agreement giving the family representation on a committee that reviews requests to use HeLa genetic data. But perhaps the most important recognition has been the telling of Henrietta's story as a human story, not just a scientific one. She's no longer just Hella, a label on a test tube. She's Henrietta Lacks, mother of 5, wife of David, a woman who loved to dance and cook and laugh, a woman whose life mattered beyond her cells. As you lie there in the darkness, perhaps think about what it means to live on. Henrietta achieved a kind of immortality she never sought, never knew about, never consented to. Her cells have outlived her by decades and will likely outlive all of us. They've traveled further than she ever did, accomplished more than she ever could have imagined. But they've also lost something essential. They've lost the ability to be part of a whole person, to contribute to consciousness, to participate in the dance of life as Henrietta knew it. They're immortal but imprisoned, eternal but isolated, dividing endlessly in their glass and plastic worlds. This is what cancer does. It trades cooperation for competition, harmony for chaos, mortality for a twisted kind of forever. HeLa cells remind us that immortality without purpose, without connection, without the ability to be truly alive, might not be immortality at all. It might just be existence stretched thin across time. There's a photo of Henrietta Lacks that her family has shared with the world. She's standing with her hands on her hips, looking directly at the camera with a slight smile. She's wearing a dress she likely made herself, and her eyes are bright with life. When I think about HeLa cells, those trillions upon trillions of cells dividing in laboratories everywhere, I try to remember that photo. I try to remember that before they were immortal, they were human. Before they were HeLa, they were Henrietta. And perhaps that's the most important lesson from this story. In our quest to understand cellular immortality, in our drive to conquer disease and extend life, we must never forget the humans at the heart of it all. Every cell sample comes from a person with a story. Every scientific breakthrough is built on someone's loss, someone's gift, someone's life. Henrietta's cells achieved immortality, but at a cost. The cost of being separated from the woman they once were. The cost of becoming tools rather than parts of a living whole. They gained forever but lost their purpose. They survived but ceased to truly live. As you drift closer to sleep, carried by thoughts of cells and stars and stories that outlive their tellers, remember Henrietta Lacks. Remember that immortality comes in many forms. In the children we raise, the lives we touch, the changes we make in the world. Remember that sometimes the most profound legacy is not in living forever, but in how we live the time we have. And somewhere tonight, in thousands of laboratories around the world, HeLa cells are dividing. Each division a heartbeat Henrietta never felt. Each new cell a tomorrow she never saw. Each culture dish a chapter in a story that began with a young mother seeking help for pain and became something neither she nor anyone else could have imagined. The cells are immortal. But Henrietta was irreplaceable. And perhaps in the end that's the difference between merely surviving and truly living, between cellular immortality and human life, between forever and a life well lived, however brief. In cellular terms, these imperfections are mutations, tiny errors that accumulate with each division. Most are harmless, like typos that don't change the meaning of a sentence. But some can be dangerous, changing crucial instructions, turning helpful genes into harmful ones. And the more times a cell divides, the more chances for these errors to accumulate. The Hayflick limit, then, is like a library policy that says, this book can only be checked out 50 times. After that, it's retired. preserved perhaps, but no longer circulating. It's a quality control mechanism, preventing cells with too many accumulated errors from continuing to replicate. This brings us to one of the most profound realizations in biology. Cellular aging protects us from cancer. You see, cancer cells are cells that have figured out how to ignore the checkout limit. They've hacked the library system, creating infinite copies without regard for quality or consequence. The Hayflick limit is one of our body's primary defenses against this cellular rebellion. Think about it this way. Every cell division is a roll of the dice. Most of the time, nothing bad happens. But occasionally, a mutation occurs in a gene that controls cell growth. If cells could divide indefinitely, these mutated cells would have unlimited opportunities to accumulate more mutations, eventually gathering enough errors to become cancerous. The Hayflick limit puts a cap on this process. It says, "You've divided enough. Time to rest." This is why, when we look at cancer cells like HeLa, we see that one of the first things they do is reactivate telomerase, that enzyme that rebuilds the protective caps on chromosomes. They've disabled the countdown clock, removed the library checkout limit, decided to photocopy themselves into infinity regardless of the consequences. But the Hayflick limit isn't just about preventing cancer. It's part of a larger system of cellular quality control that maintains the integrity of our bodies over time. When cells approach their division limit, they don't just die. Instead, they enter a state called senescence, a kind of cellular retirement. Senescent cells are fascinating creatures. They're not dead, but they're not fully alive either. They've stopped dividing, but they remain metabolically active. They're like retired workers who no longer do their main job but haven't quite left the building. And just like retirees might take up new hobbies or volunteer work, senescent cells take on new roles in the body. In some ways, these roles are helpful. Senescent cells secrete signals that promote wound healing. They can suppress tumor formation by creating an anti-cancer environment. They play important roles in embryonic development, helping to shape growing tissues. In the short term, senescence is a graceful exit strategy, a way for cells to stop dividing while still contributing to the organism's well-being. But here's where our story takes a darker turn. While senescent cells can be helpful in small numbers and for short periods, they become problematic when they accumulate. You see, senescent cells don't just sit quietly in retirement. They become what scientists call SASP cells, cells with a senescence, associated secretory phenotype. It's a fancy way of saying they become cellular grumps, constantly complaining to their neighbors. These cellular curmudgeons secrete inflammatory molecules, growth factors, and enzymes that can damage surrounding tissues. They're like that neighbor who, upon retiring, decides to play loud music at odd hours, leave their garbage out, and generally make life difficult for everyone around them. A few senescent cells are manageable, but as we age and accumulate more of them, they begin to create a chronic state of inflammation. This accumulation of senescent cells is now thought to be one of the primary drivers of aging. They contribute to arthritis, making joints inflamed and painful. They accumulate in blood vessels, promoting atherosclerosis. They gather in the brain, potentially contributing to neurodegenerative diseases. They're in the skin, making it less elastic and more prone to wrinkles. Everywhere we look in an aging body, we find these twilight cells, not quite dead, but definitely causing trouble. It's a cruel irony, isn't it? The very mechanism that protects us from cancer in our youth becomes a source of decline in our old age. The cells that stop dividing to prevent tumor formation end up creating an environment that promotes age-related diseases. It's as if our bodies made a bargain. Protection from cancer now, paid for with inflammation and degeneration later. In cellular terms, these imperfections are mutations, tiny errors that accumulate with each division. Most are harmless, like typos that don't change the meaning of a sentence. But some can be dangerous, changing crucial instructions, turning helpful genes into harmful ones. And the more times a cell divides, the more chances for these errors to accumulate. The Hayflick limit, then, is like a library policy that says, this book can only be checked out 50 times. After that, it's retired, preserved perhaps, but no longer circulating. It's a quality control mechanism, preventing cells with too many accumulated errors from continuing to replicate. This brings us to one of the most profound realizations in biology. Cellular aging protects us from cancer. You see, cancer cells are cells that have figured out how to ignore the checkout limit. They've hacked the library system, creating infinite copies without regard for quality or consequence. The Hayflick limit is one of our body's primary defenses against this cellular rebellion. Think about it this way. Every cell division is a roll of the dice. Most of the time, nothing bad happens. But occasionally, a mutation occurs in a gene that controls cell growth. If cells could divide indefinitely, these mutated cells would have unlimited opportunities to accumulate more mutations, eventually gathering enough errors to become cancerous. The Hayflick limit puts a cap on this process. It says, "You've divided enough. Time to rest." This is why, when we look at cancer cells like HeLa, we see that one of the first things they do is reactivate telomerase, that enzyme that rebuilds the protective caps on chromosomes. They've disabled the countdown clock, removed the library checkout limit, decided to photocopy themselves into infinity regardless of the consequences. But the Hayflick limit isn't just about preventing cancer. It's part of a larger system of cellular quality control that maintains the integrity of our bodies over time. When cells approach their division limit, they don't just die. Instead, they enter a state called senescence, a kind of cellular retirement. Senescent cells are fascinating creatures. They're not dead, but they're not fully alive either. They've stopped dividing, but they remain metabolically active. They're like retired workers who no longer do their main job, but haven't quite left the building. And just like retirees might take up new hobbies or volunteer work, senescent cells take on new roles in the body. In some ways, these roles are helpful. Senescent cells secrete signals that promote wound healing. They can suppress tumor formation by creating an anti-cancer environment. They play important roles in embryonic development, helping to shape growing tissues. In the short term, senescence is a graceful exit strategy, a way for cells to stop dividing while still contributing to the organism's well-being. But here's where our story takes a darker turn. While senescent cells can be helpful in small numbers and for short periods, they become problematic when they accumulate. You see, senescent cells don't just sit quietly in retirement. They become what scientists call SASP cells, cells with a senescence-associated secretory phenotype. It's a fancy way of saying they become cellular grumps, constantly complaining to their neighbors. These cellular curmudgeons secrete inflammatory molecules, growth factors, and enzymes that can damage surrounding tissues. They're like that neighbor who, upon retiring, decides to play loud music at odd hours, leave their garbage out, and generally make life difficult for everyone around them. A few senescent cells are manageable, but as we age and accumulate more of them, they begin to create a chronic state of inflammation. This accumulation of senescent cells is now thought to be one of the primary drivers of aging. They contribute to arthritis, making joints inflamed and painful. They accumulate in blood vessels, promoting atherosclerosis. They gather in the brain, potentially contributing to neurodegenerative diseases. They're in the skin, making it less elastic and more prone to wrinkles. Everywhere we look in an aging body, we find these twilight cells, not quite dead but definitely causing trouble. It's a cruel irony, isn't it? The very mechanism that protects us from cancer in our youth becomes a source of decline in our old age. The cells that stop dividing to prevent tumor formation end up creating an environment that promotes age-related diseases. It's as if our bodies made a bargain. Protection from cancer now, paid for with inflammation and degeneration later. But remember, evolution doesn't optimize for immortality. It optimizes for reproduction. As long as we live long enough to have children and help raise them, evolution considers its job done. The Hayflick limit and cellular senescence work beautifully for the first few decades of life, keeping cancer at bay while we're young and fertile. That they cause problems later is, from evolution's cold perspective, irrelevant. But here's where our story takes an exciting turn. Scientists, being the curious creatures they are, have begun asking, what if we could have our cake and eat it too? What if we could keep the cancer protection of the Hayflick limit while preventing the accumulation of problematic senescent cells? This has led to a new field of research called xenotherapeutics, treatments designed to deal with senescent cells. There are two main approaches: and both sound like something from science fiction. The first approach is called senolytics, drugs that selectively kill senescent cells. The idea is elegant in its simplicity. If senescent cells are causing problems, why not remove them? Researchers have discovered that senescent cells, despite being growth arrested, are surprisingly vulnerable to certain compounds. They're like fortresses that have put all their energy into walls but forgotten to stock food. Strong but brittle. Early experiments in mice have been remarkable. Old mice treated with senolytic drugs show improved physical function, better fur quality, increased lifespan, and reduced signs of age-related diseases. It's as if clearing out the cellular retirees who've overstayed their welcome rejuvenates the entire neighborhood. The second approach is xenomorphics, drugs that modify senescent cells without killing them. Instead of evicting the troublesome retirees, these treatments aim to reform them, reducing their inflammatory secretions while preserving any beneficial functions. It's a more nuanced approach, recognizing that senescent cells aren't entirely bad, just poorly behaved. Some of the most promising xenotherapeutic compounds come from surprising sources. Quercetin, found in apples and onions. Fisetin, abundant in strawberries. Dasatinib, a cancer drug that turns out to have senolytic properties. It's as if nature has been hiding the fountain of youth in the produce aisle all along, though of course the doses needed for senolytic effects are much higher than what you'd get from diet alone. There are even more exotic approaches being explored. Some researchers are working on immune therapies that train the body's own immune system to better recognize and clear senescent cells. Others are investigating ways to reprogram senescent cells, turning back their cellular clocks without making them cancerous. CAR T-cell therapy, originally developed for cancer, is being adapted to target senescent cells. But as we explore these possibilities, we must remember the wisdom of the Hayflick limit. It exists for a reason. Cells that can divide indefinitely are dangerous. The history of cancer research is littered with attempts to extend cellular lifespan that ended up promoting tumor formation. Any intervention that interferes with senescence must be careful not to unleash the very cancer that senescence evolved to prevent. This is why current xenotherapeutic approaches focus on removing senescent cells rather than preventing senescence altogether. It's a subtle but crucial distinction. We're not trying to make cells immortal. We're trying to prevent the problems caused by cellular zombies. Cells that won't divide, but won't quite die either. There's something poetic about this approach. Instead of seeking immortality, we're seeking to make mortality more graceful. Instead of preventing cells from aging, we're helping them complete their journey. Sometimes, the kindest thing a cell can do is know when to say goodbye. And the kindest thing we can do is help it leave peacefully. As you lie there, perhaps feeling your own body's weight against the bed, consider the trillions of cells within you at different stages of their journey. Some are young and vigorous, dividing with enthusiasm. Some are middle-aged, working steadily but showing signs of wear. Some have reached their Hayflick limit, entering the twilight of senescence. And some are dying, making room for the next generation. This is the rhythm of cellular life. Not a march toward immortality, but a dance between renewal and retirement, between growth and rest, between holding on and letting go. The Hayflick limit isn't a flaw in our design, it's a feature. It's the cellular wisdom that says, I've done my part, I've divided enough, now it's time to step aside. In our modern world, where we're often told to be productive forever, to never slow down, to fight aging at every turn, there's something deeply wise about cells that know their limits. They remind us that there's dignity in aging, purpose in slowing down, and even beauty in the twilight years, as long as we don't overstay our welcome. Perhaps one day, we'll master the art of clearing senescent cells, extending not just lifespan but health span, the years of vigorous, healthy life. Perhaps we'll learn to help our cells age gracefully, maintaining the protection of the Hayflick limit while avoiding the inflammation of cellular senescence. Perhaps we'll find the balance between the immortal jellyfish and the mortal human, between endless division and timely retirement. But for tonight, as you drift towards sleep, take comfort in knowing that your cells are watching out for you, each one carrying its own countdown clock, each one knowing when to divide and when to rest, each one contributing to the beautiful, temporary, precious pattern that is you. They age not because they must, but because they choose to. Because sometimes, The most loving thing a cell can do is know when its story should end, making room for new stories to begin. In the morning, billions of your cells will have reached their limits. Billions more will have taken their place. And you, the pattern that emerges from this constant renewal and retirement, will wake up still you, carried forward by the wisdom of cells that know both how to live and how to age, how to persist and how to let go. Sweet dreams, carried on the wings of cells that chose mortality so that you might truly live. Now we come to what might be the most extraordinary chapter in our bedtime story of cellular immortality, the part where humans stopped simply observing nature's immortal creatures and began learning their secrets, where we moved from watching jellyfish turn back time to attempting the magic ourselves. This is the story of how we discovered that every cell in your body carries within it the memory of youth, and how we learned to whisper the right words to make cells remember. Our tale begins in a small laboratory in Kyoto, Japan, where a young scientist named Shinya Yamanaka was facing what seemed like an impossible puzzle. The year was 1999, and Yamanaka had recently returned from America, where he'd been studying to become a surgeon. But his hands, steady enough for research, trembled during operations. So he traded the operating room for the laboratory, moving from healing bodies to understanding the very essence of what makes our cells what they are. The question that consumed him was deceptively simple. Can we turn back time for cells? Not in the way of our immortal jellyfish friend, who transforms its entire body, but in a more precise way, taking an adult cell, say from your skin, and convincing it to become young again, to forget its specialization, and remember the infinite potential it had when you were just an embryo. To understand the magnitude of what Yamanaka was attempting, imagine your life as a tree. When you were an embryo, you were the seed, containing all possibilities, able to become trunk or branch, leaf or flower. Your embryonic stem cells were like this seed, pluripotent, capable of becoming any type of cell in your body. But as you developed, cells made choices. This one became a neuron, that one a muscle cell, another a piece of your heart. Each choice was like climbing out along a branch of the tree. Once a cell had traveled to the tip of the neuron branch, conventional wisdom said it couldn't climb back to the trunk and choose a different path. Scientists had achieved the reverse journey only through complex procedures, transferring the nucleus of an adult cell into an egg cell that had its own nucleus removed. This was how Dolly the sheep was cloned in 1996. The egg cell somehow contained factors that could reprogram the adult nucleus, erasing its cellular memory and returning it to a state of youth. But what were these factors? The egg cell held its secrets close, like an ancient alchemist guarding the formula for the philosopher's stone. Yamanaka decided to approach the problem differently. Instead of trying to decode the egg's complete recipe for youth, he would search for the minimum ingredients needed. He started with a list of 24 genes that were active in embryonic stem cells but silent in adult cells. These genes coded for proteins that acted like cellular switches, turning other genes on or off. His hypothesis was simple yet audacious. Perhaps, if we could reactivate the right combination of these genes in adult cells, we could convince them to forget their adult identity and remember their youth. What followed was a painstaking process of elimination that would have tried the patience of saints. Yamanaka and his team, particularly a dedicated graduate student named Kazutoshi Takahashi, began testing combinations of these genes. They would introduce them into adult mouse cells using viruses as delivery vehicles. Imagine microscopic postal workers delivering packages of youth to cellular addresses. Then they would wait and watch, looking for signs that the cells were changing, becoming younger, forgetting their specialized roles. Most combinations did nothing. Some killed the cells, others caused chaos. It was like trying to find a specific four-note melody that would unlock a magical door, but having to test every possible combination of notes. The work was tedious, repetitive, the kind of science that happens not in moments of brilliant insight, but in months and years of systematic searching. But then, in 2006, after years of work, they found it. Not 24 factors, not 10, not even 5, just 4. 4 genes that, when activated together in adult cells, could turn back the cellular clock. They named them OCT4, SOX2, CLIF4, and CMYC. bland names for proteins that could work miracles. Together, they became known as the Yamanaka factors, or sometimes, more poetically, OSKM, after their initials. When these 4 factors were introduced into adult skin cells from a mouse, something remarkable happened. The cells began to change. They lost their skin cell characteristics. Their shape shifted. Their gene expression patterns transformed. They began to look and act like embryonic stem cells. They had forgotten they were skin and remembered they could be anything. It was as if Yamanaka had discovered 4 simple words that, when spoken together, could make cells remember their youth. You are not finished. You can still become. You have choices. Remember. The scientific community was stunned. The implications were staggering. If we could take any cell from an adult body and return it to an embryonic state, we could then guide it to become any other type of cell. Skin could become neuron. Blood could become heart muscle. The branches of the cellular tree were no longer one-way paths. We had found a way to climb back to the trunk. In 2007, Yamanaka's team achieved the same transformation with human cells. They took skin cells from adult humans and turned them into what they called induced pluripotent stem cells, iPSCs. Induced because we made them this way. Pluripotent because they could become many things. Stem cells because they had regained the power to differentiate into any cell type. The Nobel Committee didn't wait long. In 2012, just 6 years after the initial discovery, Yamanaka shared the Nobel Prize in Physiology or Medicine. The committee recognized that this discovery had fundamentally changed how we understand cellular identity. Cells weren't locked into their fates. They could be reprogrammed. Time's arrow, at least at the cellular level, wasn't as fixed as we thought. But here's where our story takes an even more interesting turn. The Yamanaka factors don't just create stem cells. Depending on how they're used, how long they're activated, in what combinations, at what levels, they can achieve different degrees of rejuvenation. It's like having a dimmer switch for cellular age. Turn it all the way, and cells return to an embryonic state. Turn it part way, and something even more intriguing happens. Cells can become younger while maintaining their identity. Imagine if you could become 20 years younger, but keep all your memories, your skills, your knowledge. That's what partial reprogramming offers cells. They can shed the markers of age, the damaged proteins, the dysfunctional mitochondria, the shortened telomeres, while remaining neurons or muscle cells or whatever they were meant to be. They remember their youth without forgetting their purpose. Recent experiments have shown this isn't just laboratory fantasy. In 2016, researchers at the Salk Institute used periodic activation of Yamanaka factors in mice with progeria, a disease of accelerated aging. The mice lived 30% longer and showed signs of rejuvenation in multiple organs. Their cells had sipped from the fountain of youth without drowning in it. Even more remarkably, in 2020, researchers used a subset of Yamanaka factors to restore vision in mice with glaucoma and age-related vision loss. They activated just 3 of the 4 factors, OCT4, SOX2, and CLIF4, leaving out CMYX because of its association with cancer in the retinal cells of old mice. The cells didn't become stem cells. They remained retinal cells, but they became younger retinal cells, with restored function and renewed ability to transmit visual signals. It was as if the researchers had found a way to wind back the clock just enough to restore function without erasing identity. But the Yamanaka factors aren't the only tools in our cellular engineering toolkit. Enter CRISPR-Cas9, the molecular scissors that have revolutionized our ability to edit the very code of life. If Yamanaka factors are like a time machine for cells, CRISPR is like a word processor for DNA, allowing us to find and replace genetic typos, delete problematic passages, or insert new chapters into the book of life. The story of CRISPR's discovery is itself a tale worth telling by starlight. It began not with grand ambitions of conquering aging, but with scientists trying to understand how bacteria defend themselves against viruses. They discovered that bacteria keep a genetic memory of viral invaders, storing snippets of viral DNA like molecular mugshots. When the virus attacks again, the bacteria use these memories to guide molecular scissors, the Cas9 protein, to cut the viral DNA into harmless pieces. 2 scientists, Jennifer Doudna and Emmanuel Charpentier realized this bacterial defense system could be reprogrammed. Instead of targeting viral DNA, it could be guided to any genetic sequence we choose. It was like discovering that a security system designed to keep out burglars could be repurposed to reorganize your entire house. In 2020, they too received the Nobel Prize for this discovery. Now, imagine combining CRISPR with our understanding of cellular aging. We know that as cells age, they accumulate genetic errors, typos in the instruction manual of life. Some of these errors are random, but others follow patterns. Certain genes become silenced when they should be active. Others become hyperactive when they should be quiet. The epigenetic landscape, the system of chemical tags that tell genes when to turn on or off, becomes disorganized, like a library where all the books have been reshelved randomly. CRISPR and related technologies offer the possibility of correcting these age-related changes. We could, in theory, edit out mutations that accumulate with age. We could reactivate genes that promote cellular health and silence genes that drive inflammation and senescence. We could even insert new genes, perhaps those that give the immortal jellyfish its regenerative powers, or that allow certain organisms to produce their own vitamin C, an ability we humans lost millions of years ago. Recent experiments have shown tantalizing glimpses of what's possible. Researchers have used CRISPR to extend the lifespan of mice by targeting genes associated with aging. They've corrected genetic defects that cause premature aging syndromes. They've even begun to map the genetic differences between long-lived species and their shorter-lived relatives, identifying the genetic tweaks that might extend healthy lifespan. But with great power comes great responsibility, and perhaps nowhere is this more true than in our ability to edit the fundamental code of life. As we lie here in the darkness, it's worth pondering the ethical dimensions of these technologies. If we can reprogram cells to be younger, who gets access to this fountain of youth? If we can edit genes to prevent aging, should we? And perhaps most profoundly, if we can fundamentally alter what it means to be human at the cellular level, what do we risk losing in the process? These aren't questions with easy answers. They're the kind of questions that philosophers have pondered for millennia, now made urgent by the rapid advance of technology. Should there be a difference between using these technologies to treat disease versus enhancing human capabilities? Is there a moral distinction between helping someone with progeria live a normal lifespan and helping a healthy person live to 150? If we can edit out genetic variations that cause disease, what about variations that simply make us different? And then there's the question of unintended consequences. The genome is not a simple instruction manual, but a complex, interconnected system that we're only beginning to understand. Genes that promote aging might also protect against cancer. Cellular programs that limit lifespan might serve important evolutionary purposes we haven't yet discovered. The 4 Yamanaka factors that can rejuvenate cells include C-MyC, which is also associated with cancer when overexpressed. It's like trying to tune a vast orchestra by ear. Adjust one instrument, and the entire harmony might shift in unexpected ways. This brings us to perhaps the most philosophical question raised by cellular reprogramming, the ship of Theseus paradox at the cellular level. You know this ancient riddle. If a ship has all its parts gradually replaced, is it still the same ship? Now apply this to your body, your cells, your very identity. You are already a ship of Theseus. As we discussed in our first chapter, most of your cells are constantly being replaced. But there's a continuity. The new cells are created by the old ones, carrying forward the accumulated experiences, the wear and tear, the cellular memories of all that came before. It's like each new plank in the ship is carved by the previous carpenter, carrying forward the style, the technique, the patina of age. But what happens when we use Yamanaka factors to reprogram cells? We're not just replacing old planks with new ones carved in the same style. We're taking old, weathered planks and making them forget they were ever weathered. We're convincing them they're fresh from the tree. If we do this to enough cells, if we reprogram and replace and rejuvenate, at what point do we cease to be the same person? When does rejuvenation become recreation? These questions become even more complex when we consider the brain. Your neurons carry your memories, your personality, your sense of self. If we could rejuvenate brain cells, make them younger while preserving their connections and stored information, would you still be you? Or would you be a younger version of you, subtly different, like a restored painting that's lost some indefinable quality in the restoration? Perhaps the answer lies not in avoiding these technologies, but in approaching them with wisdom and humility. The synthetic biology approaches being developed today try to thread this needle, enhancing cellular resilience without fundamentally altering cellular identity. Scientists are engineering cells to better repair their DNA, to more efficiently clear out damaged proteins, to maintain their telomeres without becoming cancerous. It's like teaching the ship to maintain itself better rather than replacing it piece by piece. One fascinating approach involves creating cellular backup systems. Researchers are exploring ways to store pristine copies of crucial cellular components, like having spare parts ready before they're needed. Some scientists are even investigating whether we could engineer cells with redundant genetic systems, like having a backup hard drive for your cellular computer. If the primary system accumulates errors with age, the backup could restore function without erasing identity. Another approach involves enhancing cellular stress responses. Many long-lived species have cells that are exceptionally good at dealing with stress. They produce more antioxidants, repair DNA more efficiently, and clear out damaged proteins more effectively. By studying these species and using tools like CRISPR, we might be able to give human cells similar capabilities. It's not about making cells immortal, but making them more resilient, better able to maintain themselves over time. There's something beautiful about where we find ourselves in this story. We've moved from simply observing immortal jellyfish to understanding the molecular mechanisms of cellular rejuvenation. We've developed tools that would have seemed like magic to previous generations. The ability to reprogram cellular identity, to edit the code of life, to engineer biological systems with increasing precision. Yet with each advance, we're reminded of the profound complexity of life. Every cell is not just a bag of chemicals, but a historical record, carrying the traces of every division, every stress, every moment of your existence. The Yamanaka factors can erase some of this history, but should they erase all of it? CRISPR can edit the text, but do we fully understand the story we're rewriting? As you lie there, perhaps on the edge of sleep, consider that you are living in an extraordinary moment in human history. The technologies we've discussed tonight, cellular reprogramming, gene editing, synthetic biology, are not distant dreams but present realities. Somewhere in the world right now, scientists are using Yamanaka factors to create neurons from skin cells to study Alzheimer's disease. Others are using CRISPR to correct genetic defects that cause suffering. Still others are engineering cells to be more resilient, to age more gracefully, to maintain health longer. We may be the last generation to accept aging as inevitable, or the first to transcend it. We stand at a threshold, holding tools of unprecedented power, faced with choices that will shape the future of our species. Do we use these tools to eliminate disease and extend healthy life? Do we enhance human capabilities beyond their natural limits? Do we pursue immortality at the cellular level, and if so, at what cost? Perhaps the wisdom lies not in choosing between mortality and immortality, but in finding a middle path. We can learn from our cells themselves, how they balance growth with restraint, renewal with retirement, change with continuity. We can use our new tools not to wage war against aging, but to negotiate a better peace with it. We can help cells maintain their vitality longer without forcing them to forget what they've learned. We can fix what's broken without erasing what makes us human. The 4 Yamanaka factors whisper to cells, remember when you were young. But perhaps the message we should send is slightly different. Remember your strength. Remember your resilience. Remember how to heal, but don't forget your journey. For in the end, we are not just the sum of our cells, but the story they tell together. And while we now have the power to edit that story, to revise and extend it, we must remember that the most beautiful stories are not those that go on forever, but those that make their time meaningful. The goal is not immortal cells, but cells that help us live fully for as long as we're here. Tomorrow, as you wake, you'll carry with you the knowledge that your cells are not fixed in their fate. They carry within them the memory of youth and the possibility of renewal. And perhaps, in some not too distant tomorrow, we'll find the wisdom to help them age, not less but better, to live not forever but well. Until then, sleep peacefully, cradled by trillions of cells that are, even now, writing the continuing story of you. Now we arrive at perhaps the most profound questions of our journey, the ones that make even the immortal jellyfish seem simple by comparison. As you lie there in the darkness, cradled between sleep and waking, I invite you to join me in pondering not just the biology of cells, but their philosophy. What does it mean to be alive at the cellular level? What is identity when we zoom in to the microscopic scale? And perhaps most mysteriously, how does the cooperation of trillions of mortal cells create the singular, conscious experience of being you? These aren't questions with easy answers. They're the kind of questions that have kept philosophers awake for millennia and scientists humble despite all their discoveries. They're questions that become even more pressing as we develop the ability to reprogram cells, to extend their lives, to blur the boundaries between one cell and another, between self and not self, between mortal and immortal. Let's begin with a puzzle that might seem simple but opens into infinite complexity. Are you the same person you were 7 years ago? 10 years ago? When you were born? Most people would answer yes. Of course, you're the same person. You have the same memories, mostly, the same personality, evolved perhaps, but recognizably yours. The same sense of continuous existence. But here's the beautiful paradox. Almost none of the cells that made up your body 7 years ago are still with you today. Your skin has been replaced hundreds of times. Your liver has regenerated itself. Your bones have been broken down and rebuilt by armies of osteoclasts and osteoblasts. Your blood is entirely new. Even many of your brain cells, those supposedly permanent residents, have been quietly replaced or extensively renovated. You are, quite literally, not made of the same stuff you were made of a decade ago. So what makes you, you? This is an ancient puzzle that philosophers call the problem of personal identity. But it takes on new dimensions when we consider it at the cellular level. If you're not your cells, if those can be replaced without changing who you are, then what are you? The standard answer is that you are the pattern, not the matter. You are the way the cells are organized, not the cells themselves. You are information, not substrate. Think of it like a river. The Ganges has been the Ganges for thousands of years, yet not a single molecule of water that flows past Varanasi today was there even a year ago. The river persists, even as its substance constantly changes. It is a pattern of flow, not a collection of specific water molecules. You, perhaps, are similar, a pattern of biological organization that persists, even as its cellular substrate flows through time. But this raises new questions. If you are a pattern, what exactly is that pattern? Is it the arrangement of your neurons and their connections? The connectome that neuroscientists dream of mapping? Is it the dynamic flow of electrical and chemical signals that dance through your nervous system? Is it something even more abstract, the information processing that emerges from the wetware of your brain? And here's where our modern understanding of cellular biology makes things even more interesting. We now know that cells don't just carry DNA, they carry epigenetic information, chemical tags that record their history, their experiences, their cellular memories. When a stem cell becomes a neuron, it doesn't just express different genes, it accumulates a history of being a neuron. It remembers. So perhaps you are not just a pattern, but a story, a narrative written in cellular experiences, in the accumulated history of trillions of cells that have lived and died in the project of being you. Each cell carries a chapter of this story. When old cells pass their information to new cells, they're not just copying DNA, they're passing on cellular traditions, cellular culture, cellular wisdom. This is why the Yamanaka factors we discussed are so philosophically intriguing. When we reprogram a cell back to a younger state, we're not just changing its physical properties, we're editing its story, erasing parts of its history. If we did this to enough of your cells, would we be editing your story? Would you still be you if your cells forgot their journey? But perhaps we're thinking about this all wrong. Perhaps the question, what is identity at the cellular level, assumes that identity exists at the cellular level, when in fact it might be something that only emerges from the collective. This brings us to one of the most profound mysteries in all of science. How does the cooperation of trillions of individual cells create the unified experience of consciousness? Each of your cells is, in a sense, a living being in its own right. It takes in nutrients, expels waste, responds to its environment, maintains its internal organization. A cell exhibits all the hallmarks of life. If we could shrink down to cellular size, we might recognize each cell as a creature, as complete and self-contained as any organism. Yet somehow, when trillions of these cellular creatures come together, something magical happens. They don't just form a colony, like bacteria in a petri dish. They form you, a single, unified consciousness that experiences itself as one being, not trillions. How? The answer seems to lie in the extraordinary degree of cooperation and self-sacrifice that multicellular life requires. Your cells have given up their individual freedom for the privilege of being part of something larger. A muscle cell will never know the joy of swimming freely like a paramecium. A neuron will never experience the simple pleasure of dividing into two daughter cells. They've traded cellular autonomy for collective consciousness. This is where the immortal jellyfish and creatures like Hydra become philosophically fascinating. They represent a different solution to the problem of existence. Their cells maintain more independence, more potential for individual transformation. The price they pay is complexity. They'll never write symphonies or ponder philosophy or fall in love. We, on the other hand, have cells that specialize so extremely, sacrifice so completely, that they create the emergent miracle of human consciousness. Think about what your neurons have given up. In accepting their role as the substrate of thought, they've forsaken division. A neuron is born, migrates to its position, extends its axons and dendrites, forms its connections, and then, that's it. No more division, no more reproduction. It has chosen to be part of your thoughts rather than pursue its own cellular lineage. It's a profound sacrifice. Cellular immortality traded for the possibility of participating in consciousness. And it's not just neurons. Your heart muscle cells beat in perfect synchrony, subordinating their individual rhythms to the collective heartbeat. Your immune cells will literally die to protect you, committing cellular suicide to prevent infection or cancer. Every specialized cell in your body has given up possibilities to serve the whole. This cellular self-sacrifice for the collective good resonates deeply with Buddhist concepts of impermanence and interconnectedness. In Buddhism, the idea of a fixed, permanent self is considered an illusion. Everything is in constant flux, arising and passing away, existing only in relationship to everything else. Your cellular biology seems to confirm this ancient wisdom. You are not a thing but a process, not a being but a becoming. The Buddhist concept of anatman, or non-self, takes on new meaning when we consider it cellularly. Just as Buddhism teaches that what we call self is really a collection of ever-changing physical and mental processes with no fixed essence, cellular biology shows us that what we call body is really a community of ever-changing cells with no permanent substance. We are, as the Buddha might have appreciated, patterns of arising and passing away, organized into the temporary illusion of permanence. Each cell arises, exists for its brief moment, and passes away, yet the pattern persists. It's like a candle flame, constantly consuming new fuel, constantly changing, yet maintaining its form. The flame of consciousness is passed from cell to cell, like monks passing a light from one candle to another through the generations. The light continues, even as each individual candle burns out. This brings us to the question of time and how cells might experience it. We humans, with our consciousness and memory, experience time as a flow from past through present to future. We anticipate, we remember, we plan. But what about a cell? Does a liver cell experience the passage of time? Does it have any sense of duration, of before and after? At one level, cells clearly respond to time. They have circadian rhythms, molecular clocks that tick with the rotation of the Earth. They count their divisions, marking time with shortening telomeres. They age, accumulating damage and dysfunction over time. But do they experience time, or do they simply exist in an eternal present, responding to signals without awareness of past or future? The immortal cells we've discussed, the jellyfish that cycles through life stages, the HeLa cells that divide endlessly, pose particularly interesting questions about cellular time. If a cell could divide forever, would time have meaning for it? Or would it exist in a kind of eternal now, each division simply another moment in an endless sequence without beginning or end. We might find a clue in cancer cells, which have achieved a dark form of immortality. Cancer cells often have disrupted circadian rhythms. They ignore the body's temporal signals, dividing when they shouldn't, staying awake when they should sleep. It's as if in gaining immortality, they've lost their connection to time itself. They exist in a frantic, eternal present, dividing without purpose, growing without direction. Perhaps this is why cellular mortality is so important. It gives time meaning. A cell that knows it has limited divisions must make each one count. A cell that will eventually die must contribute while it can. Mortality creates urgency, purpose, meaning. Without death, there is no story, just an endless, meaningless repetition. This relationship between mortality and meaning extends beyond individual cells to the entire organism. We've seen how cells sacrifice their individual immortality for collective consciousness. But perhaps they're also sacrificing their eternal present for our experience of meaningful time. Because our cells age and die, we experience the passage of time. Because our bodies change, we have stories to tell. Because we are mortal, our lives have weight and significance. Consider what we owe ourselves for this gift. They've given up their potential for immortality so that we might think and feel and love. They've accepted death so that we might truly live. Every moment of consciousness is bought with cellular sacrifice. Every thought is powered by cells that will never divide again. Every heartbeat is a gift from muscle cells that chose rhythm over reproduction. In many spiritual traditions, there's a practice of gratitude for the body. But how often do we extend that gratitude to the cellular level? Tonight, as you lie there between waking and sleeping, perhaps take a moment to thank your cells. Thank your neurons for forsaking division to carry your thoughts. Thank your heart cells for their ceaseless rhythm. Thank your immune cells for their vigilant protection. Thank even your dying cells for making room for the new. This gratitude isn't just poetic sentiment. It reflects a deep biological truth. We are not single beings but communities. We are not individuals but collectives. We exist only through the cooperation and sacrifice of trillions of cellular citizens. In a very real sense, we owe our cells everything. And what do we owe them in return? Perhaps we owe them care. Feeding them well, giving them rest, protecting them from unnecessary damage. Perhaps we owe them purpose, using the consciousness they create for something meaningful. Perhaps we owe them acceptance, acknowledging that their mortality is not a flaw but a feature, not a problem to be solved but a gift to be honored. As we develop technologies to extend cellular life, to reprogram and rejuvenate cells, we must consider not just what we can do, but what we should do. If we could make all our cells immortal, would we still be human? If we could prevent all cellular aging, would we lose something essential about what makes life meaningful? These aren't just scientific questions, but philosophical ones, touching on the very nature of existence. There's a beautiful paradox at the heart of cellular philosophy. Each cell is complete in itself, a living being with its own drives and needs. Yet each cell is also incomplete, finding its true purpose only in relationship to the whole. It's like each cell is both a complete sentence and a single word in a larger story. Both perspectives are true, and neither is complete without the other. This paradox extends to us. We experience ourselves as individuals, separate and distinct. Yet we are also communities, collectives, ecosystems. We are one and many, self and not self, permanent patterns made of impermanent parts. We are, in the Buddhist sense, both empty of inherent existence and full of interconnected meaning. As you drift closer to sleep, carried on these waves of thought, consider how remarkable it is that you can consider these things at all. The cells that create your consciousness are pondering their own existence. Matter has organized itself in such a way that it can question its own nature. Atoms that were forged in dying stars have assembled into patterns that can contemplate infinity. This is perhaps the deepest mystery of cellular life. Not that cells can be immortal, but that mortal cells can create something that touches the eternal. Through science, through art, through love, through the simple act of wondering, we transcend our cellular limitations. We are mortal beings capable of conceiving immortality, temporary patterns capable of discovering eternal truths. Your cells don't know they're creating consciousness. They simply do what cells do. They divide and differentiate, respond and repair, age and die. Yet from these simple actions emerges the miracle of awareness. You are the universe looking back at itself, reality becoming conscious of its own existence, time contemplating eternity. In the morning, when you wake, billions of your cells will have died in the night, and billions more will have been born. You'll stretch, and trillions of cells will coordinate their actions to move your body. You'll think, and neurons that can never divide again will spark with electrical patterns that somehow encode thoughts about infinity. You'll be the same you, yet made of different stuff. You'll be proof that identity transcends substance, that meaning transcends matter, that consciousness transcends its cellular substrate. We are patterns more than particles, stories more than substances, processes more than products. We are the dreams of our cells, and they are the substance of our dreams. We are temporary arrangements of matter that have learned to ponder permanence, mortal beings that have discovered immortal truths. We are, each of us, a philosophy written in living cells, a question the universe asks about itself, a wonder that wonders at its own wondering. And perhaps that's enough, perhaps that's everything. As we near the end of our journey through the microscopic realm of cellular immortality, let's turn our gaze forward, toward the horizon where science meets tomorrow. Picture, if you will, laboratories around the world where lights burn through the night. Not because anyone forgot to turn them off, but because scientists are working with the kind of urgency that comes from being on the edge of breakthrough. They're searching for secrets that cells have always known but have kept hidden in the language of molecules and time. In Cambridge, Massachusetts, a graduate student peers into a microscope at 3 a.m., watching cells that were taken from a 90-year-old woman transform into what appears to be young, vigorous tissue. In Tokyo, a team programs a 3D bioprinter to lay down living cells in precise patterns, building a miniature liver that will soon pulse with life. In Silicon Valley, artificial intelligence systems sift through millions of genetic sequences, looking for the patterns that separate the mortals from the immortals in nature's vast library. This is the frontier of cellular immortality research. Not a single laboratory or a single approach, but a global constellation of efforts, each adding light to our understanding of how cells age, why they die, and whether those processes are as fixed as we once believed. Let me paint you a picture of where we stand today, here in 2025, at what may be remembered as the turning point in humanity's relationship with aging. The tools we've developed, CRISPR gene editing, cellular reprogramming, artificial intelligence, organ printing, are converging in ways that would have seemed like pure fantasy just a generation ago. We're not just studying aging anymore, we're beginning to intervene in it at the most fundamental levels. One of the most promising frontiers is what researchers call partial reprogramming, the art of making cells younger without erasing their identity. Remember our Yamanaka factors from the last chapter? Scientists have learned to apply them like a dimmer switch rather than an on-off button. They pulse the factors, activate them briefly, just enough to roll back some cellular damage without turning specialized cells back into stem cells. In laboratories at Harvard, Stanford, and the Salk Institute, mice treated with partial reprogramming are showing remarkable results. Their organs function better. Their fur grows back thicker and more lustrous. They run on their exercise wheels with the enthusiasm of much younger mice. Most remarkably, they live longer. Not just existing longer, but maintaining youthful vitality further into their extended lives. But mice are not humans, and what works in a controlled laboratory might not translate to the beautiful chaos of human biology. That's why the next phase of research is so critical and so delicate. The first human trials of partial reprogramming therapies are beginning, starting with specific organs and tissues rather than whole-body interventions. An eye suffering from age-related macular degeneration here, arthritic joints there. Each treatment a careful step toward understanding how these powerful tools might be safely applied to human biology. One particularly elegant approach involves targeting the epigenome, the system of chemical tags that tell genes when to turn on or off. As we age, these tags accumulate in patterns that silence youth-promoting genes and activate age-promoting ones. It's like a library where books keep getting shifted to the wrong shelves, making it harder and harder to find the information cells need to function properly. David Sinclair's lab at Harvard has developed what they call an age reversal gene therapy that can reset these epigenetic marks. In mice, they've restored vision in old eyes, reversed cognitive decline, and rejuvenated muscle tissue. The therapy uses a modified virus to deliver a specific combination of reprogramming factors directly to cells, turning back their epigenetic clocks without changing their fundamental identity. But perhaps even more exciting than turning back the clock is the possibility of replacing damaged parts entirely. This is the promise of tissue engineering and regenerative medicine, the ability to grow new organs and tissues from a patient's own cells, as young and healthy as the day they were born. Picture a future, perhaps not so distant, where organ failure is no longer a death sentence but a mechanical problem with a biological solution. Your heart is failing? We'll grow you a new one from your own cells, young and strong, perfectly matched to your body. Your liver is scarred from disease? We'll print you a fresh one, layer by layer, cell by cell. Your joints worn down by decades of use? We'll inject them with cells programmed to rebuild the cartilage, stronger than before. This isn't science fiction. Right now, in laboratories and hospitals around the world, researchers are growing miniature organs, organoids, that function like their full-sized counterparts. They've created beating heart tissue, functioning liver lobules, even brain organoids that spark with electrical activity. These mini-organs are currently used for drug testing and disease research, but they're proof of concept for something much grander. The technology for growing full-sized organs is advancing rapidly. 3D bioprinting, which uses living cells as ink to print three-dimensional structures, has already created functioning bladders, blood vessels, and patches of heart tissue. The challenge now is scaling up, moving from printing a patch of tissue to printing an entire organ, complete with its intricate network of blood vessels, its complex architecture, its integration with the nervous system. But there's another approach that might bear fruit even sooner: rejuvenating organs in place. Why remove and replace when you might be able to repair and restore? Researchers are developing techniques to deliver rejuvenating factors directly to aging organs, coaxing them back to youthful function without the need for transplantation. In one remarkable study, scientists injected elderly mice with exosomes, tiny bubbles of cellular communication, harvested from young animals. These molecular messages seem to carry instructions for youth, telling old cells to behave like young ones again. The treated mice showed improvements in muscle strength, cognitive function, and overall vitality. It was as if the young cells were teaching the old cells how to be young again. They also note that humans have always used technology to extend life. Antibiotics, vaccines, surgery, all of these intervene in natural processes to prevent death. Cellular rejuvenation therapies are just the next step in this progression. The difference is one of degree, not kind. But others argue that there's something qualitatively different about interventions that could extend life by decades or centuries rather than years. They worry about unintended consequences we can't foresee, about disrupting social contracts that have existed for all of human history, about the hubris of trying to fundamentally alter the human condition. So where does this leave us? Lying here, in the darkness at the edge of tomorrow, perhaps with a sense of both excitement and responsibility. We stand at an unprecedented moment in human history, with the power to intervene in aging at its most fundamental level. The science is advancing faster than ever before. What seemed impossible a generation ago is now being tested in laboratories. What's being tested today may be in clinics within a decade. But with this power comes the need for wisdom. We need broad public dialogue about these technologies before they arrive. We need ethical frameworks for ensuring equitable access. We need to consider not just what we can do, but what we should do. We need to ask not just how to extend life, but how to make extended life meaningful. Perhaps most importantly, we need to remember that the goal isn't just more time, but better time. The promise of cellular immortality research isn't endless existence, but healthier existence. It's not about cheating death, but about living fully for as long as we're here. As you drift towards sleep, perhaps dream of a future where your cells retain their youthful vigor longer, where your body remains strong and capable further into life, where the diseases that claimed your ancestors are prevented at the cellular level. But also dream of a future where these gifts are shared by all, where longer life means more opportunity to contribute to human flourishing, where we use our extra years wisely and well. The scientists working late into the night, searching for the secret cells have always known, are not just pursuing scientific knowledge. They're working to give us more mornings, more embraces, more moments of wonder. They're trying to give us more time to become who we're meant to be, to heal what needs healing, to create what only we can create. But in the end, whether our cells divide 50 times or 500, whether we live 80 years or 180, the fundamental questions remain the same. How do we live meaningfully? How do we love fully? How do we contribute to the grand experiment of consciousness that our cells make possible? Tomorrow, research will continue. Cells will be programmed and reprogrammed. Organs will be printed layer by layer. The secrets of the immortal jellyfish will be passed one protein at a time. And slowly, carefully, with wisdom we must cultivate alongside our knowledge, we'll extend the gift of healthy life. But tonight, as your cells continue their ancient dance of division and differentiation, of aging and renewal, perhaps simply be grateful for the time you have. Be grateful for the cells that choose mortality, so you might be conscious. Be grateful for the scientists working to give you more tomorrows. And be grateful for this moment, suspended between what was and what might be, carried by cells that know both how to live and how to die, how to persist and how to let go. The future of cellular immortality isn't just a scientific question, it's a human question. And the answer will be written not just in laboratories, but in how we choose to use whatever time our cells give us, whether that's 80 years or 800. Sleep well, carried by cells that are even now writing tomorrow into being, one division at a time. And so, my dear fellow traveller in the realm of the infinitely small and infinitely profound, we arrive where we began, with a question that seemed simple when we first asked it, but which has revealed itself to be as complex as life itself. Is death optional? When we started this journey together, perhaps you were lying in bed, eyes heavy with the promise of sleep, mind open to wonder. Now, after travelling through the microscopic landscapes of your own body, after meeting the creatures who've conquered time and the cells who've forgotten how to die, after pondering the price of immortality and the gift of mortality, we return to this fundamental question with new eyes, new understanding, new appreciation for the profound complexity hidden in those three simple words. We've journeyed through the microscopic oceans where jellyfish turn back time, transforming from adult to polyp in an endless cycle of renewal. We've watched in wonder as Turritopsis dornii performs its cellular magic trick, every specialized cell remembering how to be young again, every adult feature melting back into potential. We've seen how this tiny creature, no bigger than a match head, has solved a puzzle that has haunted humanity since we first became aware of our own mortality. We've sat beside laboratory benches where human cells, freed from the body's constraints, divide endlessly in their plastic worlds. We've heard Henrietta's story, how a young mother seeking treatment for pain unknowingly gave birth to an immortal line of cells that would outlive her by decades, travel further than she ever could, contribute to medical breakthroughs she never imagined. We've grappled with the ethics of cellular immortality, achieved without consent, benefits reaped without acknowledgement, scientific progress built on unrecognized sacrifice. We've learned the names of the proteins that whisper youth to aging cells: OCT4, SOX2, KELF4, and CMYC. The Yamanaka factors that can convince a skin cell it's an embryonic stem cell again, that can turn back cellular clocks without destroying cellular identity. We've watched as molecular scissors edit the very code of life, as CRISPR technology promises to rewrite the typos that accumulate in our genetic instruction manual, as scientists inch closer to negotiating a new deal with aging itself. We've pondered the paradox of cells that must die, so that we might truly live. We've understood how the Hayflick limit, that cellular countdown clock, protects us from cancer, even as it ensures our eventual decline. We've seen how senescent cells accumulate like cellular retirees who've overstayed their welcome, spreading inflammation and dysfunction even as they protect us from tumors. And what have we discovered? That the answer to our question isn't a simple yes or no, but something far more beautiful and strange. Death, it seems, is optional at the cellular level, but life, in its wisdom, often chooses it anyway. Think back to our immortal jellyfish, drifting in warm seas, cycling between youth and age whenever conditions demand it. For Turritopsis dohrnii, death is indeed optional, a choice to be postponed indefinitely through the miracle of transdifferentiation. When threatened, when injured, when facing the natural decline of age, this remarkable creature can simply start over. Every muscle cell remembers how to be a stem cell. Every nerve cell can forget its specialization and return to pure potential. Yet even these tiny immortals can die. They can be eaten by fish, infected by parasites, poisoned by pollution, stranded by storms. They found a loophole in mortality, but they haven't escaped the fundamental vulnerability of being alive. They're immortal in the way a river is immortal, constantly renewing, constantly flowing, but still subject to drought, to damming, to the myriad forces that can interrupt the flow. And perhaps that's the first part of our answer. Immortality and invulnerability are not the same thing. Cells can learn to divide indefinitely, to repair their DNA with perfect precision, to rebuild their telomeres like a road crew constantly repaving a highway. But they remain part of the physical world, subject to its laws and limitations. They can refuse the internal clock of aging, but they cannot refuse existence itself. Remember, our HeLa cells, achieving a kind of immortality Henrietta Lacks never sought, dividing endlessly in laboratories across the world. They've escaped death, yes, but at what cost? They've lost the ability to be part of a whole person, to contribute to consciousness, to participate in the full experience of human life. They're immortal but isolated, eternal but limited, forever reproducing but never truly living as Henrietta lived. In their plastic dishes, they divide and divide and divide, each generation identical to the last, or nearly so. They've achieved what alchemists dreamed of, what Ponce de Leon sailed to find, what humanity has sought in myths and legends since we first understood that we die. Yet they've also lost something essential, the ability to be part of something greater than themselves, to contribute to the emergence of consciousness, to participate in the dance of life as Henrietta knew it. They can't form tissues anymore, can't organize into organs, can't create the complex structures that made Henrietta who she was. They're like a single note played forever. Continuous, but not music. Present, but not alive in any meaningful sense. They've gained eternity, but lost purpose. Achieved deathlessness, but sacrificed everything that makes life worth living. This points to the second part of our answer. Immortality without purpose, without connection, without the ability to contribute to something greater than oneself, might not be a gift, but a curse. The cells that learned to live forever also lost their reason for living. They gained eternity but lost meaning. Consider the wisdom of the Hayflick limit, that cellular countdown clock that says to each cell, "You have 50 divisions, give or take. Use them well." At first, this seemed like a cruel restriction, a flaw in our design. Why would evolution build in an expiration date? Why would life choose to limit itself? But we've learned it's actually a protection against cancer, against the accumulation of errors, against the chaos that comes when cells forget their place in the larger symphony. Each division is a risk, a chance for mutations to creep in, for the careful orchestration of the genome to falter. By limiting divisions, the Hayflick limit says, better to bow out gracefully than to risk becoming a monster. And here we find the third part of our answer. Sometimes, choosing death is choosing life. By accepting mortality, cells enable the complex, beautiful, conscious life that emerges from their cooperation. Your neurons chose to never divide again, so they could carry your thoughts. They made a bargain. We'll give up immortality, but in exchange, we'll create something immortality alone could never achieve. Consciousness, memory, the ability to ponder these very questions. Your heart cells chose synchronized beating over solo performance. In the embryo, they started as individual cells, each with its own rhythm, its own pace. But as your heart formed, they learned to listen to each other, to sync their beats, to create the unified pulse that would drive your blood for a lifetime. They gave up their cellular autonomy for the privilege of being part of something that could love, that could race with excitement, that could ache with loss. Every specialized cell in your body chose limitation so that you might have no limits on what you could think, feel, create, and become. Your muscle cells chose contraction over contemplation. Your kidney cells chose filtration over flight. Your skin cells chose protection over possibility. Each accepted a narrow role so that you, the collective, could have broad horizons. This brings us to perhaps the most profound realization of our journey. We exist only because our cells know how to die. It sounds paradoxical, even cruel, but it's written into the very structure of multicellular life. Without programmed cell death, apoptosis, that cellular swan song we discussed, you wouldn't have fingers. They'd still be connected by webbing, like a duck's foot, because the cells between your digits wouldn't have known to die, to carve out the spaces that make grasping possible. Without cellular turnover, your skin couldn't protect you. The outer layer of your skin is made of dead cells, keratinocytes that have filled themselves with protective proteins and then died, creating a barrier between your living interior and the harsh world outside. They're cellular martyrs, dying so that deeper cells might live. Your blood couldn't carry oxygen without cellular death. Red blood cells are born in your bone marrow, but as they mature, they expel their nucleus, the very heart of the cell, the instruction manual, the possibility for repair or reproduction. They become cellular zombies, alive but unable to divide, unable to repair themselves, living only to carry oxygen until they wear out after 120 days. They sacrifice everything that makes a cell, becoming instead perfect oxygen delivery vehicles. Your immune system couldn't adapt to new threats without cells willing to die. When your body fights an infection, immune cells multiply rapidly, creating armies to battle invaders. But once the threat is gone, most of these cells must die. If they didn't, if they kept multiplying, kept attacking, they'd turn on your own tissues. Autoimmune diseases often arise when immune cells forget how to die on schedule, when the army doesn't stand down after the war is won. Without the willingness of cells to step aside when their time comes, there would be no room for growth, no space for renewal, no possibility for the constant becoming that is life. Every day, billions of your cells die, and billions more are born. You are less like a statue, fixed and permanent, and more like a whirlpool, a stable pattern maintained by constant flow, constant change, constant renewal. They embody the deepest spiritual truths, without needing to understand them conceptually. They practice non-attachment by letting go of their potential for other fates. They demonstrate interconnectedness by functioning only in relationship to other cells. They show us that ego, the desperate clinging to individual existence, is the source of suffering, while acceptance of our role in the larger whole is the path to meaning. Tomorrow, when the sun rises and your cells wake you with their coordinated activity, you'll face choices. How to spend the finite divisions remaining to your cells. How to use the consciousness that their cooperation creates. How to honor the sacrifice of the neurons that can't regenerate, the heart cells that beat faithfully, the immune cells that die defending you. This passage serves as a gentle, philosophical meditation on how to honor the cellular sacrifice that enables human consciousness, ultimately concluding that the meaning of life lies not in avoiding death, but in living fully within our finite time. The text begins by offering practical ways to care for our cellular community. When we choose nourishing foods over processed ones, exercise regularly, or prioritize adequate sleep, we're not just making healthy choices, we're honoring trillions of voiceless cells that depend entirely on our decisions. Each healthy choice is framed as a gift to these living beings that have sacrificed their individual potential to create our consciousness. The passage then contemplates how we might use this gift of awareness that our cells provide. Having given up their own immortality so we could think, feel, and wonder, our cells deserve to have their sacrifice honored through meaningful action, whether through love, creativity, understanding, or helping others. Even simply marveling at our existence is presented as a worthy response to this cellular gift. A significant portion addresses the work of scientists researching cellular immortality, clarifying that their goal isn't to defeat death, but to negotiate a better relationship with it. They seek not endless life, but better life, more time to grow, heal, and contribute. Their work on clearing senescent cells and reprogramming aged cells aims to extend health span rather than mere lifespan, making our finite time more vital and meaningful. The text then transitions into poetic territory. describing humans as miracles of cooperation and symphonies of cellular jazz. We're portrayed as the universe's way of experiencing itself, ancient stardust that has evolved the capacity to dream and wonder. This cosmic perspective emphasizes that we are not separate from the universe but active participants in its self-discovery. The passage explores the paradox of immortality through mortality. While our physical cells will return to earth, water, and air, perhaps becoming parts of shells, cliffs, or even new stars, the patterns we create through love, beauty, and understanding echo forward through time. Every person we've helped, every child we've taught, every friend we've comforted, carries cellular memories of our influence. This is presented as a more meaningful immortality than mere cellular division. The concluding sections offer a profound reframing of death and meaning. We're told that being temporary makes us precious, being mortal makes us meaningful, and being finite makes us free. The beauty of life's symphony lies not in its endlessness, but in its form and movement, its journey from silence through song back to silence. The passage ends with blessings and gratitude, encouraging the reader to greet each day with purpose and joy. It reveals the ultimate secret our cells have always known. Life isn't about avoiding death, but about making death meaningful. Existence isn't about lasting forever, but about mattering while we're here. We are simultaneously life discovering what it means to be, consciousness exploring its own nature, and mortality finding meaning in limits. The final metaphor presents each human life as a song in the cosmic symphony, with the gentle command, "You are that song, sing well." Your neurons are firing in patterns that somehow, miraculously, mysteriously, despite all our scientific advances, we still don't fully understand how create the experience of lying in bed, of listening to words, of pondering infinity. They long ago gave up the ability to divide, accepting cellular mortality in exchange for the privilege of participating in consciousness. Right now, as you process these thoughts, neurons that will never reproduce are spending their precious energy to help you understand. Think about the profundity of that sacrifice. Your neurons could have remained stem cells, maintaining their youth, their potential, their ability to become anything. Instead, they chose to become something specific, carriers of thought, weavers of consciousness, the substrate of every memory you've ever formed and every dream you've ever dreamed. They chose meaning over immortality, purpose over persistence, depth over duration. Your heart cells are beating in perfect synchrony, lub-dub, lub-dub, a rhythm they've maintained since before you were born and will maintain until your last moment. They've subordinated their individual rhythms to create something greater, the pulse that drives life through every corner of your being. Each beat is a choice, a cellular vote for cooperation over competition, for the whole over the part. Consider the democracy of your heartbeat. No single cell commands the rhythm. Instead, they listen to each other, respond to each other, create their beat through consensus. It's a cellular symphony where every player is both conductor and musician, leader and follower, individual and collective. They've achieved what human societies struggle with: perfect cooperation without losing individual identity. Even your dying cells deserve recognition, perhaps especially your dying cells. Right now, millions of them are packaging themselves up neatly, sending signals that say, "I'm ready to go." Please recycle what you can. Thank you for letting me be part of this. They're dying with dignity, with purpose, making room for fresh cells to take their place. Their death is not a failure, but a gift, the final contribution of a cellular lifetime of service. They're not dying randomly or chaotically. They're following a program encoded in their DNA, a death that's as carefully orchestrated as their life. They break their DNA into neat fragments. They package their contents into tidy vesicles. They display signals on their surface that say, "Eat me," to passing immune cells. They die so quietly, so efficiently, that you don't even notice. No inflammation, no drama, just a graceful exit that maintains the harmony of your cellular society. Compare this to necrosis, cell death by injury or trauma. When cells die violently, they burst open, spilling their contents, causing inflammation, triggering immune responses. It's cellular catastrophe. But apoptosis, programmed cell death, is cellular poetry. its death transformed into an act of love, a final gift to the community of cells that continue. I want to thank you, yes, you, lying there in the darkness, for joining me on this journey through the microscopic universe within you. When we began, perhaps you saw yourself as a single being, an individual separate from the world around you. Now, I hope you see yourself as you truly are, a vast collaboration, a cellular civilization, a walking ecosystem of cooperating lives. Together, we've explored questions that touch the very heart of existence. We've met creatures that refuse to age, the immortal jellyfish cycling through time, the hydra with its endless supply of stem cells, the tardigrades that pause their very existence when conditions become unbearable. We've seen how each found a different answer to mortality, a different way to persist through time. We've met cells that can't stop dividing, HeLa cells carrying Henrietta's genome, but no longer Henrietta's purpose, cancer cells that have forgotten the cellular social contract, stem cells that maintain their potential at the cost of never becoming. We've seen how immortality without purpose becomes not a gift but a kind of cellular purgatory. We've learned about scientists working to unlock the secrets of cellular youth. Shinya Yamanaka discovering the 4 factors that can turn back cellular time, researchers using CRISPR to edit the mistakes that accumulate with age, visionaries imagining a future where aging is not inevitable but optional. We've seen the promise and the peril of these technologies, the hope they offer and the questions they raise. We've pondered what philosophers have wondered for millennia, but can now ask with new precision, what is identity when every part of you can be replaced? What is consciousness when it emerges from cells that die and are reborn? What is the self when the self is actually a multitude? But most of all, we've discovered that we are not solitary beings but communities. We are not individuals but collectives. We are, each of us, a universe of cells, each one choosing, moment by moment, to be part of our story. We are consciousness emerging from cooperation, meaning arising from mortality, stories written in the living language of cells. As you drift off tonight, carried toward dreams on the gentle rhythm of your breathing, remember that you are participating in something ancient and ongoing. You are part of an unbroken chain of cellular life that stretches back nearly 4 billion years. The cells in your body carry molecular memories of the first cells that learned to divide, that discovered how to capture energy from sunlight, that invented the miracle of DNA. The calcium in your bones was forged in the heart of a dying star, a star that had to die so that you might live, stellar mortality, creating the very elements that make cellular life possible. The iron in your blood once flowed in the core of that star, and before that existed as pure energy in the first moments after the Big Bang. You are, quite literally, made of cosmic history. The water in your cells has been cycling through clouds and seas for billions of years. The same molecules that hydrate your neurons once fell as rain on dinosaurs, once formed the first oceans where life began, once existed as ice in comets that bombarded the early Earth. You are an eddy in the endless circulation of water through time. The DNA in your nucleus carries edits and annotations from countless generations of ancestors, stretching back to the very dawn of life. Every cell division, every generation, added notes to this epic manuscript. Some pages were lost, others duplicated, others edited for clarity or efficiency. You carry in your cells the solutions to billions of years of problems, the accumulated wisdom of everything that learned to live. You are stardust, temporarily assembled into this particular pattern, this specific consciousness, this unique perspective on the universe. And while the pattern is temporary, while your cells will age and die and return their elements to the cosmic recycling bin, something about you touches the eternal. The love you've given doesn't die when your cells do. It lives on in the neural patterns of those you've loved, in the cellular memories of comfort and connection. Every kind word you've spoken has literally rewired someone's brain, creating new synaptic connections that wouldn't exist without you. You've edited the cellular structure of everyone you've ever touched with kindness. The beauty you've created, whether a work of art, a well-cooked meal, a garden tended with care, a problem elegantly solved, has changed the world in ways that ripple outward through time. Someone saw what you made, and it altered their neural firing patterns, which influenced their actions, which touched other lives, which created further ripples. You are already immortal in your effects, even as your cells count down to their limits. The understanding you've gained becomes part of humanity's collective knowledge. Every insight, every realization, every moment of clarity adds to the vast project of consciousness understanding itself. When you learn something true about the world, you're not just educating yourself, you're contributing to the universe's self-awareness. Through you, the cosmos knows itself a little better. The small kindnesses you've offered, holding a door, sharing a smile, listening when someone needed to be heard. These aren't just social niceties. They're evolutionary victories, proof that consciousness can transcend the selfish imperatives of individual cells and choose compassion. Every time you've put another's needs before your own, you've honored the same sacrifice your cells make every moment of every day. In the grand symphony of the universe, perhaps the most beautiful notes are the ones that know when to fade. A song that never ended wouldn't be a song, it would be noise. A story that never concluded wouldn't be a story, it would be meaningless repetition. A life that never ended might not be a life at all. It might be existence without growth, presence without purpose, time without meaning. Your cells understand this in their molecular wisdom. They divide when division serves the whole. They specialize when specialization is needed. They age when aging protects you, and they die when death makes room for renewal. They are, in their own way, perfect Buddhist practitioners, accepting impermanence, embracing change, finding meaning not in permanent existence, but in their contribution to the flowing river of life. So, perhaps the question isn't whether death is optional, but why life chooses it anyway. And the answer, written in the language of cells across billions of years of evolution, seems to be this. Death gives life shape. Without endings, there are no stories. Without limits, there is no meaning. Without mortality, there is no urgency to grow, to change, to contribute while we can. Death creates boundaries that make meaning possible. Imagine a painting that extended infinitely in all directions. Would it still be art? Or would it just be everything and therefore nothing? Life needs edges, needs frame, needs the creative constraint of limitation to become something more than mere existence. Death enables the turnover that allows adaptation. If the first cells that ever lived were still here, taking up all the space, using all the resources, there would be no room for innovation, no possibility for evolution. Life explores possibility through generations, each one a new experiment, a new combination, a new chance to find better solutions to the challenge of existence. Death provides the urgency that drives purpose. If we had infinite time, would we ever get around to saying, "I love you"? Would we ever pursue our dreams with passion? Would we ever feel the bittersweet beauty of a sunset, knowing that both we and the sun are temporary phenomena in the cosmic dance? Death makes room for the new while honoring the old. Your cells carry forward what matters: the DNA, the molecular machinery, the cellular wisdom accumulated over billions of years. But they also know when to let go, when to pass the torch, when to trust that the next generation will carry on the essential work of being alive. As you lie there tonight, cradled between consciousness and sleep, I invite you to feel, really feel, the miracle of what's happening inside you right now. This isn't metaphor or poetic exaggeration. This is the literal truth of your existence, more wondrous than any fairy tale, more magical than any myth. Trillions of cells are working in concert to create this moment of awareness. Trillions. That number is so large it loses meaning. So let me make it more real. You have more cells in your body than there are stars in the Milky Way galaxy. You have more cells than there are grains of sand on all the beaches on Earth. Each one is a living entity, and all of them are choosing, moment by moment, to be you. Some are at the peak of their vitality, dividing with youthful enthusiasm. In your bone marrow right now, stem cells are differentiating into fresh blood cells, some becoming red cells that will carry oxygen, others becoming white cells that will patrol for invaders, still others becoming platelets that will rush to seal any breach in your vessels. They're choosing their fates, accepting their roles, embracing their contributions to your story. Others are in their cellular middle age, working steadily at their specialized tasks. Your liver cells are right now breaking down toxins from your dinner, synthesizing proteins for tomorrow, storing energy in the form of glycogen. They could, theoretically, activate telomerase, and divide indefinitely. They have the genetic capability. The instructions are there in their DNA, just silenced. But they don't. They choose to age and die on schedule so that your liver can maintain its architecture, its function, its integration with the rest of you. Think about that for a moment. Your liver cells have the secret to immortality locked in their genetic vault. They could unlock it. They could become like healer cells, dividing forever. But they don't, because immortality for them would mean death for you. They choose mortality so that you might live. They choose limitation so that you might thrive. They choose to be part of your story rather than to write their own endless, meaningless tale. Still, others are approaching their limits, preparing to pass their responsibilities to the next generation. In your gut right now, epithelial cells that have spent days absorbing nutrients, defending against pathogens, maintaining the delicate balance of your microbiome, are preparing for their final act. They'll detach from the intestinal wall, journey through your digestive system, and exit your body, having given their all to keep you nourished and protected. They don't fight this fate. They don't activate emergency immortality protocols. They accept their role in the greater story, play their part, and exit gracefully when their scene is done. They understand, in their molecular wisdom, what we sometimes forget, that the show must go on, and that means some actors must leave the stage. And all of them, every single one, is choosing to be part of your story.